Hello everyone, this is Brock Skaggs, and I'm going to make a continuation of a video that I started earlier. You can see the work I've already done in the first video where we were looking at this shaft. It's under a torsional loading. It's kind of got two segments to it, segment AB and segment BC there. And in our first video we were trying to determine the maximum torsional shear stress experienced by each section of the shaft. And so we went through, found the internal torque carried by each section of the shaft, and that's something we'll again use in this video. So just to recap that, what we did was drew free body diagrams, making the cuts in kind of the middle regions of the shaft there. Always took the left-hand sides, if you will, away from that fixed connection at C. Used our equilibrium equations and determined that the torque carried by AB is 20 foot-pounds or 240 inch-pounds, and the torque carried by BC is 30 foot-pounds or 360 inch-pounds. If you have questions on that part of it, I'd suggest you go back and look at the previous video. We were using those in order to calculate the maximum torsional shear stress in each shaft, where we were using this tau max is equal to TC over J equation. It's also associated with task 1. The second part of the problem was, okay, now that I know the shear stresses, can I determine the angle of twist of the entire shaft? And so basically what I'm saying is point C here is going to be fixed against the wall, so it's not going to rotate. But point A here is out on its free end. I've got these two isolated torques, one at A and one at B, that are trying to twist the shaft in different directions. Well, at the end of the day, point A, let's say a point on this extreme surface, or extreme face, is going to rotate clockwise or counterclockwise by a certain amount. How much is that? And by a certain amount we're talking about with respect to point C, which is way back on the opposite end of the shaft. We call that the angle of twist of this shaft. I'm going to call it theta AC here. And so our kind of very basic formula that we're going to be looking at here is going to be something like theta, the angle of twist, is TL over J times G here, where we've got the torque, the length of the shaft, J is the polar moment of inertia again, and G is the shear modulus. And we said this thing was made out of aluminum, so G is 3.75 times 10 to the 6 psi. And so the problem we're going to run into here is the fact that in order to use this very simplified form of the equation, in the length considered, the other three variables have to be constant. And those other three variables are the torque, the polar moment of inertia, and the shear modulus. Or excuse me, the shear modulus, the G value. And so in order to deal with that, here I've got to split this into two separate problems. The reason being is because my sections AB and BC, well, they both have different cross sections, so the polar moment of inertia is going to also be different, and the torque is different, right? One's carrying 240 inch-pounds, the other's carrying 360 inch-pounds. And so we're basically going to split this problem up into two subproblems. It'll say something like the angle of twist of the entire shaft is the angle of twist of the first part of the shaft plus the angle of twist of the second part of the shaft. And I just have to be careful on the plus part because I might have to subtract here if they're going in opposite directions. And when we get there, we'll talk about a sign convention. And so that's going to be the process we kind of take down here. And so I'll just kind of split the screen up a little bit here and continue forward. We have AB on the left-hand side, BC on the right-hand side, so I'll go ahead and adopt that as well. And so here we'll calculate the theta AB, if you will, which will be the angle of twist of A relative to B. And so here I'll just say, well, theta AB is TL over J times G, so it's the torque in AB, times the length of AB, all over the polar moment of inertia, JAB, and divided by G, our shear modulus there. And so I'm not putting the subscripts on G because it's common between the two of them. Other than that, I should know all the variables right here, as far as already explained them and have numerical values, including G as well. And so I'm just going to plug and chug here. TAB is 240 inch-pounds, so that'll come down here. The length of AB up here at the top is 2 feet, so 24 inches. Notice I'm getting all my length units to inches. The polar moment of inertia, this is a solid circular cross-section. It's right here, pi over 32 d to the fourth, where the d value is 1 inch to the fourth, and the G is 3.75 times 10 to the sixth. And so we should be able to compute a value here. And so just grabbing my calculator, 240 times 24 divided by, and then the denominator is pi over 32 times 1 to the 4th, which is just 1, times 3.75 times 10 to the 6th. I'm getting here approximately 0.0156, we'll say. And units here should end up being in radians. All the length units should fall off. The force unit, you have the pounds in pounds per square inch, and the pound up here should fall off as well. And so we end up with an angular unit of radian coming out of this formula. The other thing I want to tag onto this thing is the direction. Shaft segment AB, the question is, okay, from a certain perspective, and again, I always draw my eyeballs here, so when I'm talking about angle of twist, I'm talking about looking at it from this perspective way out here. Is it rotating clockwise or counterclockwise? And so I usually look at the free body diagrams first. And so on this free body diagram here, one way to think about it is that internal torque, TAB, think of that as clamping down, holding the material in that section, and then looking at the other torques that are implied on it. Well, here I've got T sub A going in the counterclockwise direction. That's the only one there. So this segment of the shaft will also rotate in the counterclockwise direction. And so with that, I'll come down here and just make a note. Hey, this is moving in the counterclockwise direction there. Another way to think about it is that the segment of the shaft, as far as the direction in which it's going to be rotating, will always be in the opposite direction of the internal torque. And so the internal torque here, I've got it drawn as clockwise. In my free body diagram, I got a positive number for my equilibrium equation, so that confirms that the direction was right. And so since this TAB is directed clockwise, this segment of the shaft, segment AB, is going to be rotating counterclockwise there. And so two different ways in order to get the same interpretation. And so this just represents the angle of twist of A relative to B. And so A relative to B here, so that first segment. Now we just need to repeat the process and look at B relative to C. And so I'll do that on the right-hand side here. Again, we're having to split this up because the torque is changing between the two sections as well as the polar moment of inertia. And so I'm going to have here something like theta BC is equal to the torque BC, the length BC, all over JBC and G. And then we just start filling in the values. 360 inch-pound was the torque carried by this section. The length of BC, I believe, was 3 feet or 36 inches. The polar moment of inertia changes a little bit because it's pi over 32, d to the fourth minus d to the fourth. That's right here. So it's actually this expression right in the denominator above, 1.25 inches to the fourth minus 1 inch to the fourth. And then the G value is 3.75 times 10 to the sixth psi here. And so I've got all of the values filled out here. Now time to calculate the magnitude of this rotation. So 360 times 36 divided by, you've got pi over 32, 1.25 to the fourth minus 1 in there, and the G value as well, 3.75 times 10 to the sixth. And here I'm getting roughly 0.0, so again quite small numbers, 2 and 4. We'll just go to 4 decimal places as well. Again, units on that's going to be in radians. So that's the magnitude, but how far have I rotated, clockwise or counterclockwise? So again, I can look at my free body diagram here. Let's look at the internal torque. The internal torque is directed counterclockwise on the diagram. We confirm that by finding that we have a positive value coming out of our equilibrium equation, so that is correct direction. And so that means section BC is actually rotating in the opposite direction of the internal torque, and so in this case being clockwise, and so this is actually geared clockwise, again being from the eyeball perspective down here in the lower left. The other alternative way to look at it would be, hey, TBC is holding it still, it's clamping it on there. You got T sub A rotating counterclockwise with, I believe it was 20 foot-pounds. TB is bigger. It's got 50 foot-pounds pulling in the clockwise direction, so there's going to be still a net torque trying to rotate BC in the clockwise direction, albeit smaller than the TB value. Either way gets us the direction for this clockwise rotation of segment BC. And so here you've got AB trying to rotate counterclockwise, BC is rotating clockwise. Well, what happens between A all the way relative to C is really the question we're after. And so to do that, we use a little bit of superposition. And so here we're going to say something like theta AC is equal to the theta AB plus the theta BC. And then here we need to introduce a sign convention. Our sign convention here I'm going to write as counterclockwise is positive, which is a common one here. And so that way when I write theta AB, it's 0.0156 radians. And then I have plus theta BC. Well, theta BC, though, is a clockwise, so it's got to be a negative value. So it'll be plus a negative 0.0244 radians. So plus my negative 0.0244 radians. Again, that's because of the direction in which theta BC is rotating. And so grab my calculator and make this computation. I'm getting approximately negative 0.0088 radians. It's a positive, or no, it's a negative value, excuse me. So this thing is going in the clockwise direction there, because we've got that negative sign right there, and that's tying me into this clockwise rotation. Other thing, maybe I asked for it in degrees instead of radians, so there I could come down here and say, well, 0.0088 radians, one way to convert is 180 degrees is pi radians. And so just come through here, 180 divided by pi, that's roughly 0.5 degrees. And again, that's moving in the clockwise direction there. And so I guess final answer being what I've got boxed right here. Basically half a degree in the clockwise direction for the overall angle of twist of the shaft, theta AC there. And so I believe that brings us to a close. Again, we're using some superposition here. Basically, we had to break the overall length of the shaft into two segments in order to use this formula here, because the torque, the polar moment of inertia, and the shear modulus all had to be constant in the length considered there. And so thank you for watching the video. Hopefully this helps you with your mechanics and materials work, and in particular shafts loaded in torsion.